One of the areas of strong industrial collaboration that we have on campus is IMES, the Institute for Medical Engineering and Science. And within IMES is the Medical Electronics Device Realization Center. That's a center that about a decade ago was co-founded by myself, Charlie Sodini, and Joel Voldman, really looking at how we better connect the medical device manufacturers with the semiconductor industry, and doing that collaboratively at MIT, where we bring in technologists, we bring in the business folks that understand there's a market, and we bring in the clinicians that understand there's a clinical need. And so as part of that, we collaborate with all the hospitals in the greater Boston area. MIT benefits in some way from the fact that we don't have a hospital, so we collaborate with all the hospitals in making sure that we can get pilot technology into the clinical environment. My graduate students and graduate students of many other investigators spend a lot of time over at Mass General Hospital, at the VA, at Brigham and Women's, at the Children's Hospital, understanding the clinical workflow, understanding the clinical need, and getting the experience of what it means to design a device or technology that needs to fit within clinical care and clinical practice. And one of the areas that we've been quite successful in deploying not only technology, but impacting clinical care and collaboratively educating clinical fellows and MIT PhD students is in the area of ultrasound, and improving broadly the usability and diagnostic capabilities of ultrasound, reducing the time that it takes to train a sonographer, reducing the amount of time that it takes for a sonographer to get the quality image that they need to get. Within the context of ultrasound imaging, one of the things that we've been exploring for a number of years now is how do we broadly reduce the variation associated with acquiring imagery? How do we measure and control the acquisition state of ultrasound imagery? So for example, if you are acquiring an image of the carotid artery or any tissue that's near surface, depending on how you're interacting with the tissue, how the probe, the ultrasound probe is touching the body, that interaction, that force that's being applied during the imaging process will distort the tissue. Knowing how much you're distorting the tissue or distorting the tissue in a controlled way allows us to correlate the deformation that we're seeing from the ultrasound with how hard we're pressing, and to more robustly extract the mechanical properties or the physical properties of the tissue, whether that be the elasticity, the speed of sound, the acoustic attenuation. The other thing that's quite important is knowing where on the body you're acquiring an image. If you watch a sonographer in their scanning process, they'll go through this hunting process of moving the probe around, in their mind developing a mental model for what the volume is that they're imaging, and then they'll find the one slice that is of interest and acquire that image. But to interpret that image, they really needed to go through that process of moving things around. So we're able to add imaging technology, cameras, small cameras and light sources to the outside of the probe that look at the outside of the body, that look at the skin features on the body, the micro reliefs, the texture of the follicles, the texture, the variation of the melanin, and use the variation and map of the body, of the skin, to know how the probe is moving around, and actually also to know where the probe is in an absolute sense on the body, to use those skin features to be able to put the probe at some point in the body, to take it away, and a week or a month or several months later to bring it back and get it back to the same location. So in this way we can measure and control the position and orientation, again reducing the variability that's typically inherent to how imagery is acquired. So we've put all these technologies together to now allow us to get better data that now allows us to be more thoughtful in extracting information out of the imagery, and actually allows us to learn a lot more from the imagery once it's been acquired in a very controlled and low variability way.